Alright, this is going to be just a quick presentation on the second derivative as an application of the derivative. We've talked about the second derivative a little bit, and we basically know that to find the second derivative, we would just take the derivative of the derivative. And the notation that we use for second derivative, instead of saying f prime like we would in the first derivative, notice that this is f double prime is the second derivative. The other thing that's very important that you understand about the second derivative is what it does. So look at this statement. It says the second derivative gives us the acceleration, which is the rate of change of the rate of change, how fast the derivative is changing. We don't do too much with graphing in this course, but it's nice to know just that when a graph changes from concave up to concave down, that point is called the point of inflection. We talked about this a little bit in our opening unit. But what happens is this is actually the point at which the second derivative is 0. Let's do a couple quick examples of the second derivative. So here, the daily oxygen consumption of a turkey embryo increased from the time the egg is laid through the time the chick hatches. In a brush turkey, the oxygen consumption can be modeled by. All right, so I'm going to write this for you because it did not transfer very well. So this function is actually C of t is equal to negative 0.028 t cubed plus 2.9 t squared minus 44t plus 95, where t is going to represent time, and we know it's going to be time in days since the egg was laid. It typically hatches around 50 days. Okay, well, I do want to go ahead and rewrite our function one more time because it did not transfer in this file very well. So negative 0.028 t cubed plus 2.9 t squared minus 44t plus 95. So if you read each of these, find the daily oxygen consumption 40 days after the egg was laid. There, I'm basically just asking you to evaluate the function at 40. In B, find the rate at which the oxygen consumption is changing 40 days after the egg was laid. Well, think about what that is. Now we know that that's going to be the derivative, the rate at which the oxygen consumption is changing 40 days. Then we talk about acceleration in part C, and that's where we would use the second derivative. And here are my calculations for those three values, C of 40, C prime of 40, and the thing that I want you to really notice is the label for C double prime. It's changing at a rate of negative 0.92 milliliters of oxygen per day per day. Think about what that means to make sure that you're understanding that it's the rate of change that our first derivative is changing, or the rate of change of the rate of change of 40. Let's try one more. So this one I'm going to go ahead and rewrite as well. S of t is equal to 100 plus 10t minus 0.8 t squared. And it's simply saying, what is the acceleration? So, in order to find the acceleration, you know that you would find s prime of t and then s double prime of t is the one that would tell us the acceleration. before we look at the solution to this, look at the problem and see if you will understand what the rate is going to be for our acceleration. Go back and read it if you have not read it, and then as we go into the next slide, making sure that you understand what the rate for the acceleration would be represented as. Okay, so if you read the problem now, you're probably understanding that the original rate is in meters per second. So our first derivative basically says that 10 minus 1.6t meters per second would be our instantaneous rate of change at any value of t that we were looking at in the domain. So our second derivative, well, when we take the derivative of 10 minus 1.6t, we simply end up with negative 1.6 meters per second for the acceleration. Okay, so here is the last example that we're going to look at. And again, my exponents did not transfer very well to this program, so just so that you don't get confused, I want to make sure that I rewrite the function. Okay, so in this problem, as we read it, annual sales of bottled water in the United States in the period from 1993 to 2003 could be approximated by R of t is equal to 17t squared plus 100t plus 2300, where t is the time in years since 1990. Were sales accelerating or decelerating in 2000, and how fast? Okay, so I think pretty clearly you know that if we're talking about acceleration or deceleration, we know that that's going to involve r double prime of t. So take a couple seconds, find the first derivative, and then find your second derivative, and we'll come back together and see how we can answer this question. Okay, so hopefully you have had the time to find the first derivative and the second derivative, and you can look at the first derivative here and understand that with our first derivative, that's basically going to be our original instantaneous rate of change, and we've got a function 34t plus 100. That would tell us, however we substituted in our value of t, we would take on that time. I think it was from 1993. So in this case, if we were looking for instantaneous rate of change, we could find that simply by substituting for t. But notice that we're looking for the acceleration. Well, the acceleration comes from the second derivative, and we say that it is accelerating because it's a positive value, and it's a positive 34, which tells us that in 2000 the sales of bottled water is accelerating at a rate of 34 million gallons per year.